In this interview, we speak with Sergio Caprara, Associate Professor in Statistical Mechanics and Solid-State Physics at the University La Sapienza in Rome. Our discussion ranged from superconductivity to how modern science is done and many other topics. Enjoy it! Good afternoon.
Good afternoon.
I'm happy to have you here.
I'm happy too.
Yes, and we are actually taking some time off the university in the Sapienza, so we're hosted here in the historical building of Fermi, where Fermi taught. The building itself is called Marconi, but it's a historical place, right?
Really, it is. Yes.
And it has also a museum that you're curating, if I'm not wrong.
Yes, I was appointed director of this museum 1 year ago. Well, more or less 1 year now.
So we're now at December 2020, so the year of the COVID, you...
Yes, I was so lucky because I could finally succeed in getting 5 students to take care of the museum, to have it open during all the days of the week. And then the pandemic came and I had essentially to close the museum.
Sure.
It's not open to public now, essentially.
Yes.
Very small groups can visit it, but it's mostly closed to public.
Okay, but that's actually a piece of history that you now have the time to curate better or like rearrange maybe something.
Yes, and we are doing actually.
Yeah.
We are now renovating the website and trying to make possible a virtual visit of the museum.
That's really great.
That should be a first step in this direction. It's not the final one, but I think that starting from next January, it will be possible to visit our museum virtually.
Okay, that's it's 21st century altogether,
yes,
right?
altogether.
Okay, so I wanted to ask you something. You are a physicist. I mean, in many ways, we have introduced you in our audience before, but you're a physicist especially for solid-state physics.
Yes.
And especially condensed matter.
Yes.
Right. But you also, and that's the question I want to make you speak a lot of languages.
Yes, this was an old passion of mine, so I like languages as not only, because they allow me to talk to people, but also because they are very nice and very interesting in themselves. Actually, I like the structure and the dynamics and the rules and all.
That's something I want to stay in, because I wanted actually to start asking you, how many languages do you master? Like you would say, it's like you're native. You have no difficulty finding anything or writing in them.
So there are different levels. So the first I learn, and so the one that I most commonly speak is English, of course, besides my mother tongue, of course.
Then Italian?
Which is Italian. Then, of course, English is the first I learned. Then when I was a postdoc in France, I had a very crash course in French, just without taking any lecture, just on my own. I bought some books and some comics, and I started learning words and sentences, and then I was able to master some French. Then I was, this was a very old passion of mine, it was Russian. Russian I can read and listen without problems. I can watch a movie in Russian without problem. I'm not so fluent in speaking because I have not so many occasions to talk, and so my Russian is not so fluent, but I can read a book in Russian. Physics in Russian is not a problem. And understand.
Yeah, so that's actually the next thing is like how many languages you understand, and as you said already, for the French, for example, that you practiced, you use possibly some analogies that exist from your mother language.
Yeah,
right?
There are many analogies and many differences. So this is one nice aspect. For instance, another language that is exactly at the same level as Russian is Spanish. With Spanish, I can fully understand. I read books, several books. I'm not so fluent in speaking, again, because I need practicing. And so, but I can watch movies in Spanish without problem. I can read books, even classics, and without problems. Portuguese is to a lesser extent, the differences are more, so yes, but again, I have read books in Portuguese without many problems. Then there is Swedish, okay, again.
So you can follow a Swedish conversation?
Yes. Swedish is a further step behind, so I was there for, I would say, 7 months, so I could formulate very simple sentences and I could read newspapers.
And this was during, your postdoc.
This was my second postdoc. I had two postdocs abroad. One was in Grenoble in France, and the other was in Stockholm, Sweden. And so there I took the occasion to learn some Swedish. So I have several Swedish books I can read and, yes, understand.
Okay, actually, I had another question, but you forced me to ask you another question now, because I read recently some of your papers. I mean, of course, very fastly, so I would ask you more about it. So there is a paper that you co-authored, and this is called about the law of non-law.
Yes.
So let's read the title to be correct. So the paper is with Vulpiani. So
yes.
It's Caprara Vulpiani, sorry.
Yeah.
Law without law or just limit theorems. And one of the things that you are discussing in the paper is if it's possible that the part of physics can be understood only by following regularity principles, right?
Yeah.
So a bit of information,
yeah.
and not necessarily building a theory behind it. Am I getting correct? So
that is something that is another side part of my work. We with Angelo Vulpiani, we understood that we have this in common. We like to understand the theories and models which are parts of our work, of course, but we use them in everyday physics. But we want to understand more about their content and meaning at a basic level. What are models? What are they useful for? And so we ran into this proposal of Wheeler's, which in his Nobel Prize speech was talking about laws without law, as an idea that maybe some parts of physics can be just the result of some regularity that we can understand without a pre-existing theory.
So like a pattern?
Yeah, like patterns. Like patterns.
Which, for example, could work, as you saw, as you already experienced in languages, for example?
Yeah.
And of course, we are making some mistakes at the first time that we try to transfer this model, let's say, to another. It's not model, I'm using the wrong word. But using this pattern and extracting it to another language, it doesn't always work, right?
Yeah, it doesn't always work.
But the humans are the ones who are communicating, so sometimes they can make the corrections themselves, right? Like
but
but in physics, it's not the same.
The question about language is a very old and very interesting one. There is Noam Chomsky that proposed that there should be some basic underlying grammar that is common to everybody, but the issue is very controversial. The issue is very controversial.
Okay.
Is there a general basic model for all, which is valid for all languages? The question is...
It's very complicated. It's out of our expertise.
It's very controversial.
How do you say? It's unfortunately, it's out of our expertise. But the physics that you're touching you are touching this topic from a different point of view. So please let us know more about it.
So the idea is very, very tempting, I would say. The answer... The provisional answer that with Angelo Vulpiani we give is mostly negative. In some way, we say, okay, whenever you find some regularity, there is an underlying principle, which is usually a principle which, for instance, is at work whenever you deal with statistics. And so you have some theorems, very solid limiting theorems, that describe how a certain distribution for for a given set of data emerges from the statistical properties of this. So, in the end, whenever we find or detect some regularity, this can, in all the cases that Wheeler analyzes at least, there is an underlying limit theorem that supports that regularity. So it's not out of nowhere, in some sense, but there is some theory behind or something we can understand behind this regularity. So our answer is that models are useful. They cannot be thrown away just because we can take the data, analyze the data, and that's it. Of course, we can learn something just by looking at the data, but having a theory, or at least a scheme, to understand, organize, explain the data, is, in our opinion, of course, this is an opinion, important in science, in physics, and in science in general.
Therefore, that's actually very, let's say, relevant to what is happening right now with the data mining techniques.
Yeah.
That because we arrive at the point, or we try, or we thought we arrived at the point that we have enough data to do data mining on them using basically regression algorithms and simple analogies, as you say, and patterns that we can detect across a long time series or across large space scales, for example, or across basically big data sets, let's put it very generally. But this aspect that you bring forward is that we can still find patterns, but it could be that sometimes it's wishful thinking to find a pattern, right? And there is no theory supporting that underneath always. Can we find patterns without a physical law? Could it be a thing?
So what is my personal understanding about this is that, of course, you can find some patterns in some series, and there are time series that have rather regular patterns. This is, for instance, the tides. Making a forecast for the tides is very simple because the regularity is really, of course, then we have understanding of why tides are so regular and how the tide works. But in principle, you can imagine of making predictions about the tides even without a theory, okay? Just following the regularity. Now, let's move to weather forecast. Can you ever imagine that based on some analysis of time T series? So you study the weather of 100 years ago to now, and then predict the weather for the next 100 years or something. It's not thinkable, I mean. So why? Because as soon as the space of parameters widens, immediately the idea that we can follow all the patterns without a scheme becomes unthinkable, in my opinion. So detecting regularities in whenever the phase space, let's call it like this, the phase space, the space of parameters is not large enough, of the system, is not so large, then it's rather easy, of course. But as soon as the space widens, then immediately it becomes impossible, because we know that there exists something like deterministic chaos, even in dynamical systems. So tiny variation in the initial conditions can produce very, very huge effects in the future. So even even if we believe that there is some deterministic law, which may be the case or maybe not, we don't know. But even if we really believe that the world is deterministic in some sense, when we face phenomena that are ruled by deterministic chaos, then of course making prediction in the long run, it's out of,
yes. You have to know the time scale of the system.
Yeah, exactly.
You can predict, or let's say, give a probabilistic estimation that is in a confidence level that people understand, and it's useful for the next day.
Yeah,
right?
sure.
Because in the end, it goes back to application.
Yeah.
If what you know in physics is useful for someone.
For instance, we know that for planets, this works just fine. We can predict the position of a planet.
Yes, but yet not after some billion years. Right?
Not after some billion years, because there again, there is a time scale, which is now much longer than the time scale for weather forecast. But nonetheless, there is a time scale for the planets too. Yes, of course.
But yeah, let's make an analogy here for those who are not familiar with with all the planetary science and the physics, and of course ourselves, we are familiar with only a small piece of the science in any case. So what we say is that we don't know and we cannot predict, let's say, the position of Earth. Even if we know that Earth was formed 4.5 billion years ago, we still don't know, 4.2, still we don't know at the exact position that it was around our star. That's interesting. We know that it was there, but we don't know exactly where.
Yeah.
Right?
Yeah, exactly.
Okay, so let's go a bit to more to your topic, actually. Let's approach a bit your topic. And talk a bit about the superconductivity aspect. So can you explain in simple words for someone who hears it for the first time, what is the superconductivity phenomenon? We're talking superconductivity of electricity, of charge, right?
Yes. So this was my starting topic as a student in this university. This was my thesis project, and at the master level and then at the PhD level. At that time, new materials, new superconductors were discovered with some unusual properties, and so this marked the initial steps of my scientific career. So a superconductor is a material that is able to conduct electricity without generating dissipation or heat. So Usually when you run a current through a metal, a conductor, a metal, a piece of metal, then this heats up because running a current through it produces some production because of the electrical resistance. Then there is some friction in the motion of the current through the metal, and the effect of this friction is to produce heat, like all frictional processes, and so the piece of metal heats up.
So you lose energy.
And you are dissipating energy because you are somehow part of the energy that you need to run the current through the metal is dissipated into heat that goes to the environment and increases the entropy of the universe. So this is a superconductor is a material that, because of the emergence of some quantum phenomenon, can carry a current without dissipation. So in a superconductor, you can have dissipationless current flowing through it. This phenomenon, being a quantum phenomenon, is only reachable at low temperature. And usually this low temperature means really low in
terms of absolute zero, as you said, close to absolute zero.
So for most materials that were known up to the 80s of the previous century, this was really close, rather close to absolute zero. It was 10 or 20 degrees above absolute zero. And then this breakthrough arrived when I was a student of new materials with much higher, still below.
Is the cuprates?
The cuprates. So the cuprates are materials, the first materials that would and do turn superconducting even above the temperature of liquid nitrogen.
Which is minus 77, I don't know.
Plus 77 above absolute
plus
zero.
77,
77 Kelvin above absolute zero, yes. And that was, of course, a breakthrough because making experiments under liquid nitrogen is much easier than making experiments with liquid helium. It's much less expensive. But also from the point of view of technological application, of course, this was, many people saw the possibility of developing devices based on high temperature superconductivity. So the search for room temperature superconductivity is active even to this very day. There are claims that some materials under very high pressure can become superconductors at room temperature. Of course, the question is still debated, but this is just to mean that this topic is very hot and very hotly debated even to this day.
Hot in the sense we arrive at room temperature, right?
Hot in the
this
sense
is good for us. And also, you're referring to the paper in October 2020, right?
Yes.
Of Snyder et al.
Yes,
in
exactly.
Nature.
Yes.
Okay. Actually, I had a question on that because, as you said correctly, there was the room temperature. So this took place at about 15 Celsius.
Yes.
And at a very high pressure, which exceeds the pressure we have at the bottom of the mantle of the Earth. So
yes.
the bottom of the mantle, we have 140 gigapascal.
And this is 106.
I think even more. We are close to the core, but not really at the core.
Yes.
So this was reproduced by a team that used very expensive experimental apparatuses,
yes.
right? The diamond anvil.
Diamond anvil technique.
Cells.
This is the only way you can possibly produce such a huge pressure. Of course, the pressure is exerted on a tiny spot by the anvil. And of course, making experiments in this condition is very tough. So their merit is undoubtable. It cannot be doubted because, of course, the experiment is difficult in itself. About the claim, of course, there are still discussion about, because, of course, the measures are not uncontroversial, because they are difficult, of course, and so there may be explanations for the results that do not involve superconductivity. The question is debated. Of course, most people believe that this is really superconductivity happening there, but the debate is on. So we will see.
Yeah, we will see, actually. So that's one part. And coming from there, actually, it was interesting for me to read. First of all, it's interesting for me to note here that when you say high temperatures, you mean, for example, we're referring at 70 degrees above absolute zero.
Yeah.
And when I would say high temperatures, because I'm studying lava planets, I would talk about 4,000 Kelvin. So one comment I want to make here is the fact that even among physicists, when we say such words like high temperature or low temperature or high pressure, for example, for atmospheric scientists, high pressure is just 300 bar. 300 bar is a lot of pressure for atmospheric scientists.
Yeah.
And this is actually very interesting because among us even, we need to know where we come from.
And what is our reference?
What is our reference?
This is what I keep teaching to my students whenever I touch topics like this. I keep saying that small and large in physics means just nothing. You have always to refer to some level, and then you can say if something else is large or small with respect to that quantity.
Exactly.
And so the same is for temperature. So being 10 or 20 kelvins, which is degrees above absolute zero, the standard temperature for conductivity, reaching 80, or now even without going to the last developments, even 180 is a huge leap. So this is really high temperature, of course. This is still chilling cold if we compare to the temperature on the surface of the Earth. Yes.
Yes, and not leaving aside the greenhouse effect that we're not even going to touch now.
No.
So let's talk about labels in science then. I would like to ask you about the distinction that I have heard since my early years as a researcher, and it was between experimentalists and theorists.
Yes.
And the question here is, why do we separate the two if, in any case, for the scientific method, we need to do both? So a scientist should be able to perform an experiment,
actually,
and then see a theory, compare against the theory.
This is very sad, in my opinion. This is not strictly true, but we used to say that one of the last scientists that could master both experiments and theory was Enrico Fermi, actually. He was a very, very good, I would say, top quality theorist and a very, very good top quality experimentalist at the same time. Then, in some sense, it happened, or it seems that it happened, that you need to be really specialized. And once you get really specialized in the theory, you lose contact with the experiment and vice versa. So it seems that it is just a request of the excess of specialization that is demanded to do physics now. I can speak for myself. When I was a student, I was, of course, committed to do theory. I liked theory very much. So from the very first day I put my foot in this department, I was sure that I would be a theorist. But I always liked to be in a lab. I enjoyed it, and I was rather good, I would say, even in lab. And I really, even today, I like to go to visit labs, and I like to do experiments of my own, of course, and not on the scale of the real experiments of today, which are very, very complex and very, very complicated, and mostly require very, very expensive and complicated machinery to be run. But so there is not an obstacle in principle that I could be at the same time an experimentalist and a theoretician. But of course, the limitation is mostly that I have 24 hours a day, like everybody, and I cannot possibly accommodate theory and experiments in the time I have. So it's really a matter of the extreme specialization that is nowadays requested for a physicist. But I regret, in some sense, that I cannot run myself some experiments that I would really like to run.
And do both.
But I have strong and very close collaboration with several experimentalists, so I really like to discuss first-hand experimental results. This is something that is a privilege for me, because it's not like doing experiments that would be much better, but at least I can work on very, very first-hand experimental data, and that is very, very, very good for me and very exciting.
But that's interesting that you say you would like to do both, but the time is not enough.
Yeah.
So for a researcher that starts now, the time is a huge, is a currency right now.
Yeah.
Is how you decide to use your time as a young researcher, and that's why sometimes what we do in the Lectures Without Borders, because it's extra volunteering time of giving some lecture, of course, not in the level of scientific audience, but a bit more vulgarized in a way. Divulgazione, I think the word is popularized.
Yes.
It's considered a very high risk move because an early career researcher has a lot of demands from their environment, And I guess it gets more with the years, right? It was more maybe than 20 years ago that you were...
Yeah, in my opinion, although I see that it's difficult to contrast all this, it is really regrettable, in my opinion, because it would be nice, and in my opinion, it would also be an advantage for the advancement of science, that young people would be given time to meditate and not just publish and publish and publish under a pressure that, of course, it's ever more important in the early stages of scientific career, because now if you don't have a sufficient number of papers, you don't have a progression in your career, and then, of course, this is a major problem for young researchers now. Yeah. This is regrettable, in my opinion.
And this actually adds to the teaching possibilities. Teaching is also considered like a black hole when all the effort and time goes to waste in terms of material that can come out as publishable.
Yeah.
But you yourself, you have been teaching for about 18 years now.
Yes.
At least, I guess you have already started explaining physics to your peers much earlier.
Yeah.
But officially, let's say 18 years, sorry. And this is something that you were also awarded recognition from the University of Sapienza. So can you tell us a bit about the teaching and why your students like you so much? Like why they want to work with you? Because I remember that I had discussions in the corridors and people still remember master thesis that they did with you and they're happy about it.
So this is perhaps not a real merit of mine, because this is just the way I think a university professor should work. Personally, I believe, and that was clear to my mind from the very first day, I wanted to take a university career. I was really sure about this, because I saw in the university the possibility to match my curiosity for scientific research and my commitment to transferring knowledge to young people. Because in principle, if you are committed to research only, then you can work in some research institution. You are not, of course, obliged to lecture, and that would be much better. So I know that there are colleagues of mine that consider that lecturing is bothering and takes times that could be devoted to research and to publish more papers. I beg to differ. In my opinion, if you have a position at the university, you should comply with both the needs of scientific research, of course, but also of teaching to young people. And this commitment, fortunately enough, is seen by my students. So whenever I talk to them, they tell me that they appreciate a lot the effort. I'm not always successful, I must say it, but at least I make the effort to be clear, to state things in the clearest possible manner, and to try and reach every single student, not just the good ones. Reaching the good ones is always easy, because they are good. They would be good even without myself.
They are motivated.
They are motivated, they are good, they can just read physics of books and learn by themselves. So my commitment is to keep their curiosity alive while at the same time reaching also the other students. And these commitments requires a very, very huge effort. Very huge, because I must meditate all the time, weight every single word I use, weight every single teaching strategy I introduce in my course. It takes a lot of time, but I would never do in a different way. This is just the way I like to teach, and so this is perhaps not a merit, it's just the way I am. I cannot possibly be different from this.
I like actually your approach also, because a lot of times you use storylines for explaining phenomena or guiding the students through phenomena. Yeah. And I could see this in a thesis for the physics of the ice.
Yeah.
And the question that the student tried to answer there is how does patinage work? Like, am I calling it correctly? In English it is...
I think it's skating.
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 Yeah, exactly, thank you. Ice skating. Ice skating. And the story that goes in the thesis is actually a story. It's like, let's check this hypothesis, if it is the explanation. And maybe it is not, because this and this doesn't fit. Now let's move to the next hypothesis. So the storytelling has a part in learning science.
It does. It does. It does because, in my opinion, of course, if you read a book, in books you find the ideas that survived the scrutiny of the experimental tests. And so, usually one has a very, very strange impression that scientific knowledge is just a process that goes in a single direction. So there is a path which is the scientific knowledge. But if you look into the details of how each single step was taken, then you see that there were times where something was totally unclear, and maybe people were just turning around and not finding the way to overtake a difficulty. And then there were theories that were proposed, and then they died out because they had no matching with the empirical reality, and so on and so forth. So, of course, when I teach physics, I teach the part that is settled and that is universally agreed upon, but I also like to transmit to the students the idea that physics is not always clear and straightforward as it seems. But this is exactly what makes it exciting, because in some sense, producing science, physics, but science in general, requires a lot of ingenuity, of course, but in my opinion, also some artistic sense. You have to somehow push some ideas that seem at the beginning to be very inconsistent, and then little by little you find that the pieces just get together, and then all of a sudden you start seeing more clearly that there is a light at the end of the tunnel, and so that maybe this is a good direction for the advancement of science. But this does not come all of a sudden. This comes little by little by adding pieces, and then perhaps even some wrong piece, and then you go back and then you try again. So I try to convey to my students this idea that science is not something that is rigid, regular, fully predictable from the very beginning. Of course, at the end we know the result, and we could even say, oh, this was predictable. But we know only at the end that it was the case. We do not know in advance at the beginning.
It is similar to what we are living now, to make an analogy with contemporary, because for the virus that we are trying to face globally now, we say, but we knew that it was not that dangerous, or we knew that it didn't have so good transmissibility. Why did we act in this way? And that's a very big fallacy that we can easily put ourselves into, because we are disregarding the fact that we are not the people, 8 months ago, we were not the people and the knowledge that we are today.
Sure, definitely. We know today something more that we didn't know 8 months ago.
Exactly. And I wanted to ask you also something about the other award, because once we enter your office, we see a lot of awards, a lot of books, I must say, and also another award. This was given by the American Physical Society, and this is for being an outstanding referee.
Yes.
And that was just last year, 2019.
Yeah.
And I wanted to ask you about this. Why? Because the process of publishing science and what you just described, the process of trying to put together a scientific hypothesis that is rigid, and then, of course, submitting it to the peer community for review, right? The process of review. Can you tell us a bit about this review? Because it's not known to the public. How does science get accepted? How do we discuss among us? And how do we say, okay, this team found that, or this team found this, and now we know this thing about the world? So can you tell us about the review process and how
this is a crucial aspect of science, the peer review process, which means that all scientific papers are reviewed by peers, which means other scientists. And in my opinion, this is the only way things can work. So whatever hypothesis may be the best one should be scrutinized by somebody else, and before passing to the community should be really deeply analyzed. And this is peer review. Of course, based on this assumption, this would take a lot of time. Being a good reviewer takes time because you have to go into somebody else's ideas. Of course, in a related field, because usually when you act as a referee, you act in a field that is your field, not another. I'm not a referee for astrophysics or for geophysics. I'm a referee for condensed matter physics or statistical mechanics, which are the subjects that I master. But of course, this takes time. So at the same time, this is a service to the scientific community. So without this commitment to review somebody else's result, all the process of the production of science would stop, or at least would be endangered, because, of course, then there is no way to tell the difference between a paper that is just published for reasons that have nothing to do with science and a paper that has solid scientific basis, rests on solid scientific basis. Now, the point is that little by little, other things that should not have to do with science, strictly speaking, are creeping into science. Why? Because scientific publication is, of course, a matter of science, but also a matter of economy. Mm-hmm. There are enterprises that publish, and of course, they have their stakeholders that want to get some money out of the process. And so, as soon as you introduce some constraints that are related to the fact that in the end you want to make business out of science, out of scientific production, then of course you see that there are advantages, but also drawbacks for this. For instance, now, much more than before, a scientific paper can be stopped not by your peers, but by an editor.
Yes, it's true.
Just because the editors say, okay, your research may be the best ever, but it doesn't match our editorial policy. Now, an editorial policy should have very little to do with science in principle. Of course, you should take care that the scientific results that you publish are sound, are relevant, are whatever. But that said, every single result should be published, provided it complies
with the scientific method.
Yes. Whereas now, more and more, you can have a paper rejected just because it doesn't comply with some editorial policies. And so I'm wondering whether this is something that we must blindly accept because, okay, the world goes like that, or maybe there is something we can do about it. I have not a definite answer, but I feel that I am dissatisfied with this interference between the economic necessities, of course, and science. There is a kind of conflict that maybe will make things worse in the future for science.
That's interesting, because we have to say here, for those who don't know, that for the scientific reviewing, as you just described, the scientists are not paid.
No, this is just, as I said, it is a service to the community.
A service to the community.
We are not paid.
Exactly. And that the community, that's an important part. Like, there is the sense of the community exists in the scientists by as soon as they start existing, let's say, as researchers, which is typically counting as the time after your PhD.
Yeah.
Right? So that's free. But there are, as you said correctly, publishing houses that take up the role of editing and putting this together into accessible material online or printed everywhere in the world. And this takes, of course, some money and some workforce, and possibly, as you just say, possibly there are other economic interests in that sometimes, right?
Yeah.
But the community feeling, that's actually something I want to keep as a good thing here, because it's not always seen in reviewing processes, and that would be one of the last questions I would have for you. So what is the thing that makes a bad reviewer, and what is the thing that makes a good reviewer? In your experience, what have you seen in the backstages of, let's say, producing science and, as you said, accepting science for the peer community? Can you tell us some experiences?
So, yes, as an author, I've been the victim of bad reviewers many times. This happens. this is a reason why I'm committed to be a good reviewer. A good reviewer must be very open-minded. So as a reviewer, I never rejected the paper just because it was saying something that I was not agreeing upon. Of course, I believe as a scientist that the scientific debate is nourished by contrast and contradiction. So unless something can be proven wrong, which is different from having a different opinion, then, in my opinion, it should be published. So as a referee, it never happened to me to reject a paper just because I was convinced that the author of this paper was following an idea or different from my idea. I had different ideas, but nonetheless, I believe that this is better for the scientific debate, that ideas different from my ideas are published and then discussed within the community. And maybe within a few years, my ideas will prevail or maybe not. And this is how it should work. As an author, sometimes I realized that some of my results were rejected just because of some prejudice about their content. Not because the referee was not able to prove me wrong, but say, okay, you are assuming this, I don't believe that your assumption is reasonable or things like that, okay? So this happened, and so also because of this, I am committed to avoid acting like that when I am a reviewer.
And also, you mean putting personal motives against?
No, I never. So one of the things I do, and this is one, I think, of the motivation why I was appointed the outstanding referee, is that whenever I write a referee report, even if I strongly differ with the author, I'm always very respectful to them. Whereas it happens sometimes, not often, fortunately, that my anonymous reviewer, unknown to me, was very, very unrespectful to me. It happened.
Possibly hiding behind the anonymity.
And that is, in my opinion, very bad, because you're hiding behind your anonymity. And so this is very bad. You should never forget that you should assume that there is intellectual honesty on both sides. Unless you believe that I'm a pirate and not a scientist. I'm doing science, so I'm intellectually honest. I try, of course, to push my ideas, but that is how science works. You should never insult me because I'm pushing my ideas. You should perhaps differ. This is, of course, acceptable, but never be aggressive because I have ideas different from yours. I'm never aggressive, whereas sometimes I've been the victim of an aggressive reviewer.
I see.
Yeah.
So that's interesting, because that's actually what the young researchers are totally, of course, they're young, they're coming first time to that, and when they get a reviewer that the first time on their first paper is aggressive in a way or another, this would discourage them in a much more impactful way than someone who's experienced and knows more or less that this can be an exception in the room.
But the machinery is somehow got trapped into a loop, because young scientists are forced to publish. The volume of publication is increasing in an uncontrolled manner. So I understand that now the editors just receive a quantity of papers that they cannot possibly handle. So I understand, even if I don't agree, I understand why they try to reject some papers even without passing them over to the reviewers. And then, since there is this necessity of reviewing so many papers, reviewers are taken even among people that are not, I would say, not so expert or not so trained with the review process. Of course, when you are young, at a certain point, you start being a reviewer, and this is normal. But it takes a while before you become a good reviewer, in my opinion, because as with everything, you should have some training, or at least self-training, if not a training. But now I would say that the mass of inexpert or non-expert reviewers is increasing, because it comes from the needs to review more and more papers. And so in my opinion, my impression, this is just an impression, is that nowadays the number of unprofessional reviews is increasing. By unprofessional, I mean very sloppy, very, very not to the point. It takes so long a time for me to write a report because I review, because I try to motivate every single statement I make. And of course, this takes a long time. And sometimes you see some report, just 2 lines without motivation, without nothing. So yeah,
yes.
In my opinion, it's true that we do this for free. We do not get paid for that, but nonetheless, we should understand that we should do this not superficially. We shouldn't do that superficially because it's a service to the community. If we say, okay, we don't get paid, so I can do that superficially, then it's better not to do it, in my opinion.
Yes, that's
if you want to do it, then do it, but please do it seriously. Otherwise, just say, okay, I'm not interested.
Don't do it at all.
Don't do it at all. Yes, that's my suggestion.
There was here this paper for the rapid, I think, communications. I looked at it more.
Yes.
Which is, this is in this rapid communication, for the physical UB, you are stating the following, that we can measure the optical conductivity of a system near the quantum critical point, but we do not necessarily call for new concepts of quantum criticality. So this quantum criticality, I guess, refers to the point where we have superconductivity.
Yes.
Right? It enters the behavior of the material is superconductive. So that again goes to the fact of basically studying very carefully the model, starting what the model says before we try to make a new model of theory. Is this the motivation?
Yes. So this paper came in a moment where the debate about the optical properties of these new high-temperature superconducting materials were being studied, and there was a debate if critical properties, in the sense of some quantum critical phenomenon, could be observed in optics. And here we make a point about this because we take the matter seriously. And at that time, this is why this is one of the papers I choose. I found a way to put this question, this issue, on a rather solid ground by proving an identity that was my main contribution to this paper. This is why I'm proud of it, because this was just something that didn't exist before and then existed after we published this paper. An identity that proved that in some cases you cannot explain or do not expect to observe critical properties in optical experiments. And we explain why they seem to disappear from the experiments, which means which doesn't mean that they are not there, but that they cannot be observed by an optical experiment. So this is different. They are there,
that is very complex,
but they do not show up in optical experiment because of some very, very peculiar cancellation.
So you basically proved that this is there, the theory still supports this phenomenon, but you should not look at it in the optical, you should look at it in another method, possibly.
Yeah, exactly. So that's saying, so let's put it in other words. There was a statement like this: since we do not see this in optics, then this rules out the possibility that there are quantum critical phenomena. And so this was an answer to this statement. This statement can be proven false because you can show that even if there are, as we assume in the model, quantum critical phenomena, there is a very, very tiny and very precise cancellation that cancels this phenomena from the optical conductivity.
Okay, so that's interesting because apparently it is combining, as we said before, in a holistic way the experiment and the theory, right? That's exactly what we described before, that you cannot really separate the two. You should know what experiment you should look into to find the theory that you are talking about.
Yes, exactly.
Right, so that's good that you have these discussions with all the experimentalists.
Exactly. So at the time there was a claim that was essentially because since we do not see this in optical experiments, then we can rule out this possibility. And our answer was not, you cannot rule out. Of course, there is a very clear-cut situation where there is a very subtle cancellation that takes place so that you don't observe a phenomenon in optical conductivity despite the fact that the phenomenon is there. So you should observe other quantities.
And that is a paper of 2007 in the
2007.
Physical Review B. And as I see here is the rapid communication. So you choose the rapid communications, and that's what you do in science. Actually, it's something that the researchers don't know, young researchers, sometimes, when we should send something to a letter, to a rapid communication, and when we should send something to a classic paper, like a research paper. So the rapid communication is something that you notice makes a huge difference in the community. What was the motivation?
So the idea is more or less this. Now the offer from coming from different journals is becoming more and more varied, but the idea is mostly this. There are scientific works that are somehow new ideas, or at least potentially breakthrough ideas. And so the idea within the scientific community is that these ideas should be communicated very rapidly because they may open new perspectives.
I think we have enough material for generations to listen to because we have also gone through a lot of different topics. And the last question for you would be, if the holy grail of condensed matter is to find the superconductivity, let's say we find it tomorrow. Assume that we find how to do superconductivity in room temperature and pressure. How would the world look different? What would you?
So actually, superconductors have many applications even today, and of course these applications are made expensive by the fact that you have to refrigerate them, and so this makes. But you have magnetic levitations and train that, of course, take advantage of this. In Japan, I know that there exist trains that run very fast based on this magnetic levitation phenomenon, which is a phenomenon that is characteristic of superconductors. One major breakthrough that I could talk about is this quantum computing issue. So the idea that we can make a quantum computer, a computer that works with the rules of quantum mechanics, that make computing much more flexible, at least within some respect, because of the larger flexibility of quantum states with respect to classical bits.
Which have 0 and 1,
which only have 0 and 1, and they are exclusive, either 0 or 1. And one possible way to make quantum computers is through this semiconductor quantum interference device, the SQUID, which, of course, now requires to refrigerate a computer, which is, of course, not desirable. So one day, if we have room temperature superconductor, we may think of having room temperature quantum computers based on superconductivity or technologies that are superconductivity based.
Okay, so that's let's look forward to it. I mean,
let's look forward to it. Yes,
because we need to solve a lot of problems a bit faster in the planet. Thank you very much.
Thank you very much for this chat. It was nice.